Welcome back. I'm Lisa Blackburn, and this is my YouTube channel about everything I want to talk about, science and math. And today we're in AP Chemistry, talking about bonding and molecular geometry, part 2, because the video cut off in the middle of class because I ran out of memory. Okay, so now we're talking about hybrid orbitals. And it is, I think I want to erase this and show it to you. Show you what happens. Okay. All right, so what it is, if you remember, we talked about last unit, we talked about this idea that when we were doing the electron configurations, that the atoms are like full or half full better than one in a mishmash. Remember that? And while we talked about that, I introduced the concept saying that carbon doesn't really do 1s2, 2s2, 2p2, because it could only make 2 bonds. Instead, it makes 4 bonds. But it doesn't just promote an electron out of 2s2. It makes it where the bonds are all symmetrical and exactly the same. It's not like it's got s bonds and p bonds. It does something else. So that's what we're talking about. So here we've got beryllium. And if we did the electron configuration of beryllium, what would it be? Y'all tell me, what's the electron configuration for beryllium? 1s2, 2s2. Atoms will only bond where there's 1 arrow, not 2. So according to this, beryllium would not make any sort of covalent bond where it shares. It would only do electron transfer, but that's not what happens. Up here we have beryllium bonded to these fluorines, so how did that happen? Well, one thing it could do is it could promote one, and it could have a 2s and a 2p, like that. It could have promotion. So this doesn't happen. And it turns out that this doesn't happen either, because can you see how balanced and beautiful that molecule is? Because nature likes balance. Instead, it does something where it mixes them, and instead of having a 2s and a 2p, it has 1s, but that has 2. They're mixed orbitals called sp2s, or sps. It mixes these orbitals, and they're no longer S-shaped or P-shaped. They're somewhere in between, and they're exactly alike. So this is called hybridization. And a hybrid is a mixture, right? If you buy a hybrid car, it can do electric and gasoline. It's a mixture, and that's what these are. So this is how it works. Mixing the s and p orbitals yields 2 degenerate orbitals. So s plus p makes these 2, and we just have them oriented 2 different ways, but they're the same shape. Now the reason why I put dx over here is because I think it's funny that they named them degenerate. It sounded to me like the old 90s wrestlers, D-Generation X, degenerate wrestlers. If you don't know about wrestlers and Shawn Michaels and Triple H and DX, then you can just pretend like that's not there. Or you can look it up. Triple H, he's a wrestler. All right, he's in DX. So here are our degenerate little wrestler atoms, orbitals that are mixed together. It's mixed like chocolate milk. Okay, so here are 2 degenerate orbitals align themselves at 180 from each other and give 90 degrees for the 2 remaining unhybridized p orbitals. And there it is, balanced, symmetrical, bonding. Can you see how that happened? You understand it? Okay, so now what about 3? So there's different ways we can look at this. sp2 and sp3 orbitals are formed from hybridization of the 1s and the 2p's. So if you had it regular, you'd have 2s filled and 1 2p. You can promote the 1 out of the 2s to the 2p, but these are not symmetrical. So instead, you get 3 sp2s, and they are all beautiful and the same and symmetrical, ready to bond. Or what about if it says P3? Here you've got 2 in the 2s, 2 and the 2p, you promote one of those from the 2s, but then make them all the same, and this is sp3. And you should love this because this is what carbon does. Carbon promotes and blends. It doesn't just promote, it promotes and hybridizes. So everything you love is based on this. You, your mama, your dog, an ice cream sundae, a diamond. Carbon does this. Your pencil graphite, all based on carbon. Okay, so this just sort of summing it up. We've got an S, a P, and a P. They get mixed and you get 3 sp2s, and that's what we see in boron tetrafluoride. Okay, they join. Here we have an S, a P, and a P. They blend together and you get carbon, and it's tetrahedron. You get 4 sp3s that are all identical. So this is mixing. And remember that the P's come on different planes. That's why they're drawn different ways. But they all get mixed together and they're exactly the same then. They're same shape. Different orientation, same shape. Can I scroll up? This is actually written there. I just wrote it again. Yes? Is it? Well, I can't hear you. Talk loud.
Can you scroll up a little bit? I think
Scroll up? Yes, that's what I wanted to do.
No, the other way.
You want to go the other way? I went to.
Just for a second. Okay. Thank you.
So those are our sp3s, then they get joined into BF3. Those are sp3s, they get joined into methane. Okay, we gotta hurry. We want to finish this. Notice it's already written there. I just wrote it again bigger so y'all can see it. See, it's written on there real little. All right. For geometries involving expanded octets, got my dog toy. That's why we have a dog. On the central atom, we use d orbitals in the hybrid. So d's can mix too, not just s and p's. And that's what you have going on here. There it is with the 3 around the middle, like that, and then with 4 around the middle, like this one. Okay? These are called hypervalent, more than 8 electron domains. Once you know the electron domain geometry, you know the hybridization state of the atom. Okay, now we're going to talk about what are multiple bonds like. So, what we've seen so far are single bonds, sigma bonds. They're characterized by strong single overlap on the bond axis. Okay, so you've got a single bond, you've got 2 S's, they do the Venn diagram, they overlap. If you were to draw a line between a radius line from the center of these spheres, there would be a line that would go right through that bond. Okay? But there's another kind of bond called pi bonds. These are double bonds, and I drew a pi because it's the same kind of pi. And you know, Pi Day's coming up this Thursday. You should get your math teachers to like bring you some pie or something to celebrate Pi Day Thursday. We're going to celebrate by having an AP chemistry test. Woo! Okay, so pi bonds are characterized by overlap above and below the axis. So here you've got 2 p's. And they're going to overlap. Remember, this is one orbital, that is one orbital. So if you have the Venn diagram, it is above and below. And it is not on the axis. So it's more like this, above and below. Single bonds are always sigma bonds because sigma overlap is greater, resulting in a stronger bond and more energy lowering. With double bonds, you can get these pi bonds. So this is an example of a pi bond. This, even though it's on top and on bottom, is one bond. It is not a double bond. For it to be a double bond, you have a sigma bond in the middle and then a pi bond on top and on bottom. And that is a double bond. And that's a little hard to imagine, but the more you think about it, it makes sense. This is one bond, one bond, one bond, double bond. Okay, for a triple bond, it's got the sigma in the middle and 2 pi's going on. So you ever seen those battery things you put them in and you have to go like that to slide the battery case around it? Anybody ever seen that? That's what it's like. You got one bond, another one in the middle. You go, the one in the middle is the battery, and the other 2 are the case, and that's a double bond, a triple bond. So there's some coffee to go with our piece of pie. Okay, so delocalized bonding. When writing Lewis structures for species like the nitrate ion, we draw resonance structures to more accurately reflect the structure of the molecule. So like it could be like that, it could be like that, it could be like that, but really it's resonance. And remember we learned that was like mixing paint. And what it would look like with the bonds is something like that. See how they're blended together? Also, we talked about resonance with benzene. And so you can draw it like that, you can draw it like that, you can draw it like that. But really it's just this blended orbitals going all the way around. Equally. See how they're equal? It's not flipping from one to the other. It's all smeared out equally and it's symmetrical. So do you think benzene is polar or nonpolar? Nonpolar. Very good. All right, that's it. Like, share, subscribe. Science is great.